Yes. Yes, in the last class we discussed about sp3 hybridization, whereas the new equivalent atomic orbitals formed are 4. That I mentioned sp3 hybridized atomic orbitals, sp3 hybridized molecules. That I mentioned is CH4, example that I mentioned CH4, AB4 type of the molecules, AB4 type of the molecules, they have ability to form this type of the hybridization, whereas in AB4 type of the molecules, CH4 is there, CF4, carbon tetrafluoride and carbon tetrachloride and carbon tetrabromide and Cl4 molecule and NH4 plus, this type of the molecules, they have ability to form. Now, how to say that this is sp3 hybridization? Just I will give the small explanation. Here s to the power of 1 plus p to the power of 3, that is equal to 4. If suppose in sp3 answer should be 4, I will give the shortcut method, that is 1 plus 3 that is equal to 4, 1 plus 3 that is equal to 4. In CH4 molecule, this is in CH4 molecule, methane molecule, this is central atom, here these are the atoms which are surrounded to the central atom. Then write this number first, that is equal to 4, 4 plus, the valence of the carbon is 4, all the 4 valences are satisfied by means of the single covalent chemical bond with that of the hydrogen atom. Therefore, the number of unpaired electrons that left, that is equal to 0. Therefore, the total answer is equal to 4. If the answer is 4, then it is sp3 hybridized molecule. In case of CCl4, whereas this is central atom, then these are the number of atoms which are surrounded the central atom, that is equal to 4. Now, the valence of the carbon is 4. The 4 valences are satisfied by means of the single covalent chemical bond with that of the 4 chlorine atoms, and hence the number of unpaired electrons that left, that is equal to 0. Therefore, the answer is equal to 4. 4 plus 0 is equal to 4. If the 4 is your answer, then it is sp3 hybrid molecule. For example, CF4, in CF4 molecule, the type of hybridization. Here, this is central atom. These are the atoms which are bonded to the central atom. First, you have to write the atoms which are bonded, total number of the atoms which are bonded to the central atom, that is 4. Then add plus. Then valency of the central atom, that is equal to 4. Then all the 4 valencies are satisfied by means of the 4 covalent chemical bond with that of the fluorine atom. Therefore, the number of electrons that left on the central atom, that would be 0. Therefore, 4 plus 0, that is equal to 4. Is it clear? Then CBr4, carbon tetrabromide. Now, this is central atom, and the atoms which are bonded to the central atom, that is equal to 4. Therefore, that is 4 plus 0, that is equal to 4. In this NH4 plus, whereas here how many atoms which are bonded to the central atom, that is equal to 4 plus, now this is the valency, that is equal to 5. Then out of this 5 valency, that is a plus 1 is there, means that 1 electron is left, that is a 4, that is equal to plus 0. Electron, number of valence electrons is equal to 5. Out of this 5, that is equal to plus 1, then that is equal to 4, that is 4 plus 0, that is equal to 4. Therefore, the type of hybridization, that is equal to sp3. If your answer is 4, then that is sp3 hybrid molecule. Is it clear? Now this is actually 5, this is 1. Plus 1 means that deficiency, minus 1 means the efficiency. That deficiency means if suppose the central atom has the X valency, if it possesses charge plus 1, then you have to subtract 1, reverse. If suppose the species is anion, you had 1 electron or 2 electron depending upon the negative charges to the central valency, then it becomes the total number of the electrons around the central atom. Is it clear? This is about the hybridization. I will give one more hybridization, that is equal to BF4 minus BF4 minus BF4 minus. Here this is central atom, this is central atom, and these are the number of atoms which are bonded to the central atom, that is equal to 4 plus. Now the valency of the boron is equal to 3. Then 3, this is minus 1 charge, minus means electron, 3 electrons plus 1 electron, that is equal to 4. Then 4 electrons, this is boron valency, that is equal to 3, and minus 1 extra charge, that is equal to add plus 1, that is equal to 4. Boron valency is 3. Over the charge we have the minus 1 extra electron is there, therefore add 1, that is equal to 4. Then 4 electrons of this boron then forms 4 covalent chemical bond with that of the fluorine, then that is equal to 0, therefore 4 plus 0 is equal to 4. Is it clear? One more is that is beryllium. Beryllium F2 2 minus F4 2 minus F4 2 minus. Now here the central atom is equal to beryllium, 4 fluorine atoms which are bonded to the central atom, therefore keep it in mind, that is equal to 4. Then plus valence of the beryllium is 2, then 2 electrons are extra, 2 plus 2 is equal to 4. All these 4 electrons that forms a covalent chemical bond with that of the beryllium, that is fluorine, therefore the net unpaired electrons that left, that is equal to 0. Therefore here beryllium, that is equal to 2 electrons, valence electrons 2 because it belongs to second group. Here 2 electrons are extra, therefore 2 electrons extra you have to add, that is equal to 2. Therefore total number of the electrons would be 4. Total number of the electrons, that would be 4. Is it clear? I will give the shortcut method. For tetravalency elements, 4 should be here. For pentavalent elements, plus 1 should be here. For trivalent elements, 1 charge will be here. Bivalent elements, 2 charge will be here. Number of electrons, valency or group number, valency, then this negative charge that becomes this one. Here the boron valency is 3 and this is 1 extra electron, 3 plus 1 is equal to 4, that matches with 4 here. Then 4 stands for sp3 hybrid atomic orbital. Here this is 5, this is plus 1, therefore minus electron, the electron that carries minus charge, minus 5 plus 1, that is equal to minus 4, this is plus 4, that becomes 0. Is it clear? Therefore in an entrance exam they ask the questions, predict the type of the hybridization or give an example for sp3 hybrid orbitals, sp3 hybrid molecules. Your answer would be either CH4 or CF4 or CCl4 or CBr4 or Cl4 or NH4 plus or BF4 minus or BeF4 2 minus. These are the molecules. They exhibit sp3 hybridization. sp3 hybridization. See, this is sp3 hybrid molecule, this is sp3 hybrid molecule, 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 sp3 hybrid molecule. All are good examples for sp3 hybridization. Is it clear? sp3 hybrid molecules. Now, next one is sp2 hybridization. sp2 hybridization. It is nothing but the process of mixing up of the process of mixing up of one number is atomic orbital and two numbers p atomic orbitals. Two numbers p atomic orbitals. P atomic orbitals is called sp2 hybridization. Atomic orbitals to give three numbers sp2 hybrid atomic orbitals. It's called sp2 hybridization. It is the process of mixing of one number of the s atomic orbital and two numbers of the p atomic orbitals to give three numbers of the sp2 hybrid atomic orbitals is called sp2 hybridization. Power of p decides geometry. Power of p decides geometry. Power of p decides geometry for all sp2 hybrid atomic orbitals. For all sp2 hybrid atomic orbitals. Hybrid molecules. sp2 hybrid molecules. Geometry or shape. Is two-dimensional. Is two-dimensional geometry. Two-dimensional geometry, that is equal to planar geometry. Three-dimensional geometry is tetrahedral geometry. Two-dimensional geometry is planar geometry. Therefore, any one of the molecules, suppose have the central atom is sp2 hybridized, then it possesses the planar shape, that is the planar molecule. Now we will take an example of the molecules. We have to take an example of the molecules. Here, one number of the s atomic orbital, one number of the s atomic orbital, one number of the s atomic orbital. S atomic orbital is spherical shaped atomic orbital. S atomic orbital is spherical shaped atomic orbital. It is a three-dimensional molecule. Three-dimensional atomic orbital. This is X orientation, this is Y orientation, this is Z orientation. But sphere has no direction. This is S atomic orbital. Plus two numbers of the p atomic orbitals. Since it orients along x-axis, it is called a px atomic orbital. This is px atomic orbital. Similarly, we have py atomic orbital and pz atomic orbital. Px atomic orbital. Here, similarly, we have mixing may be s atomic orbital with either px plus py atomic orbital, or s atomic orbital possibilities py plus pz atomic orbital, s atomic orbital with combination of px plus pz atomic orbital. Then it lists the formation of sp2 hybrid atomic orbital. It lists the formation of sp2 hybrid atomic orbital. It lists the formation of sp2 hybrid atomic orbital. The process of mixing up of the one number of the s atomic orbital and any two numbers of the p atomic orbitals. There are three p atomic orbitals, px, py, pz. Then px plus py combination, or py pz combination, or px pz combination, it leads to the formation of. Now it is in the shape of the molecule, geometry or shape, geometry xy plane, because x and y are involved. Here geometry yz plane, yz plane. Here geometry xz plane, geometries and xz plane. Is it clear? Here the pz atomic orbital is not involved in bond formation. Here px atomic orbital is not involved in bond formation. Here py atomic orbital is not involved in bond formation. Pz not involved in hybridization. Pz not involved in hybridization. Not involved in hybridization. Here in yz plane, px is not involved in hybridization. Px is not involved in hybridization. In xz plane, py is not involved in hybridization. Py is not involved in hybridization. Is it clear? Therefore, here, depending upon the type of the atomic orbitals, the direction of the atomic orbitals, we can predict the geometry which is a planar and which is present in each plane. Suppose this is x direction and this is y direction, that is z direction. Now this plane floor is called xy plane. Now suppose this is x direction, this is z direction, this plane is called as a xz plane. Suppose this is y direction and this is z direction, this is called yz plane. This is called yz plane. Now depending upon this we can predict the geometry or shape of the molecules. Now at least the formation of there is sp2 hybrid atomic orbitals. At least the formation of sp2, this is called hybrid atomic orbital. This is called hybrid atomic orbital. Here hybrid atomic orbital. Here two numbers here. Here the two numbers here. Now in the ethylene molecule formation, here three numbers of sp2 hybrid atomic orbitals. Three numbers of sp2 hybrid atomic orbitals. All the three numbers of the sp2 hybrid atomic orbitals, they orient at an angle of 120 degree with each other. It is a planar band angle. Now each carbon atom has this is carbon atom. Three numbers of the sp2 hybrid atomic orbitals. And neighboring carbon atom is again now this has one number of the electron. It 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 has one number of the electron. Because each carbon atom having three hybrid atomic orbitals, each hybrid atomic orbitals has one number of the electron. Now hydrogen having one number of the electron in s atomic orbital, and hydrogen having one number of the electron in s atomic orbital. each hybrid atomic orbital that requires one electron for the covalent chemical bond formation. Now assume this is a carbon, this is carbon, this is one more carbon, and these are hydrogen atoms. These are hydrogen atoms. These are hydrogen atoms. These are hydrogen atoms. See, one number of the carbon atom having 3 sp2 hybrid atomic orbitals. This is sp2 hybrid atomic orbital. 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 This is sp2 hybrid atomic orbital, and this is sp2 hybrid atomic orbital. This is s atomic orbital of the hydrogen atom, s atomic orbital of the hydrogen atom, s atomic orbital of the hydrogen atom, and this is s atomic orbital of the hydrogen atom. Is it clear? Therefore, now hydrogen always seeks for one electron for the chemical bond formation. Therefore, this sp2 hybrid atomic orbital that shares one electron from that of the s atomic orbital, then it leads to the formation of s-sp2 overlapping. It leads to the formation of s-sp2 overlapping. S-sp2 overlapping that leads to the formation of hydrogen carbon sigma covalent chemical bond. Now this is s atomic orbital. Now this electron from the hydrogen atom, this yellow corresponds to the electron from that of the sp2 hybrid atomic orbital. Now this is hydrogen atom, s atomic orbital of the hydrogen atom. S atomic orbital of the hydrogen atom overlaps with that of the sp2 hybrid atomic orbital of the carbon atom. Then it leads to the formation of one sigma covalent chemical bond. Last class we discussed there is an axial overlapping of the half-filled atomic orbital that leads to the formation of hydrogen carbon sigma covalent chemical bond is formed. Hydrogen carbon sigma covalent chemical bond. Covalent chemical bond that is formed. Here also sp2 hybrid atomic orbital has one electron. S atomic orbital of the hydrogen has one electron. Therefore, it leads to the formation of one. This is hydrogen atom, and this is s atomic orbital of the hydrogen atom. s-sp2 overlapping. s-sp2 overlapping hydrogen carbon sigma covalent chemical bond. Now this hydrogen carbon, this is one hydrogen carbon sigma covalent chemical bond. This is one hydrogen carbon sigma covalent chemical bond. 2 bonds are formed here. Similarly, the neighboring carbon atom having 3 numbers of the sp2 hybrid atomic orbitals. Then this sp2 hybrid atomic orbital having one electron. It always seeks for one electron for the covalent chemical bond formation with that of the neighboring atom. Therefore, here hydrogen atom, s atomic orbital of the hydrogen atom that forms one covalent chemical bond with that of the sp2 hybrid atomic orbital of the carbon atom. Therefore, here again s-sp2 overlapping. s-sp2 overlapping. It leads to the formation of one more sigma covalent chemical bond. This is called carbon hydrogen sigma covalent chemical bond. Now we have one more sp2 hybrid atomic orbital here. It seeks for one more electron for the covalent chemical bond formation. Therefore, the neighboring hydrogen atom that shares this electron, s atomic orbital of the hydrogen atom that shares electron, then it leads to the formation of s-sp2 overlapping. This is hydrogen atom, where this pink stands for the electrons from that of the hydrogen atom. Yellow stands for the electrons from that of the sp2 hybrid atomic orbital. Therefore, now we have 4 numbers of the total, that is equal to 4 numbers of the sigma covalent chemical bonds are formed. Sigma bonds or sigma covalent chemical bonds. Now we have 4 numbers of, it is equal to 4 numbers of sigma covalent chemical bond. Sigma covalent chemical bond. These are carbon, hydrogen, sigma covalent chemical bond. See, here this is sp2 hybrid atomic orbital of the carbon atom. This is sp2 hybrid atomic orbital of the carbon atom. Now these two are present along the line or along the axis. Then again they shares one electron for the covalent chemical bond formation. Then it leads to the formation of one electron from this sp2 hybrid atomic orbital and one electron from this sp2 hybrid atomic orbital, sp2 and sp2. This is also sp2 hybrid atomic orbital. Now sp2 overlapping, sp2 stands for carbon, S stands for hydrogen. sp2 overlapping, that leads to the formation of, this is a carbon sigma covalent chemical bond. This is also sigma bond, sigma chemical bond. Sigma bond, this is carbon sigma chemical bond. One number of sigma bond, that is sigma covalent chemical bond. That is most precise word. Then sigma covalent bond. This is carbon sigma covalent chemical bond. Carbon sigma covalent chemical bond. How many bonds are there? Totally we have 5 covalent chemical bonds. Carbon hydrogen sigma covalent chemical bond, 1 number. Carbon hydrogen sigma covalent chemical bond, 2 number. Carbon hydrogen sigma covalent chemical bond, 3 number. Carbon hydrogen sigma covalent chemical bond, 4 number. Carbon sigma covalent chemical bond, 5 number. Therefore totally we have 5 sigma bonds. Totally we have 5 sigma bonds in ethylene molecule. Very important. One of the atomic orbital, like that of the PZ atomic orbital, that is not involved in covalent chemical bond formation, and it is perpendicular to the plane of the x and y. It is perpendicular to the plane of the x and y. Now this is x and y. Now this is PZ atomic orbital. White corresponds to the PZ atomic orbital. It is not involved in the bond formation or hybridization, and this is perpendicular to the plane of the x and y. Perpendicular to the plane of the x and y. Is it clear? Whether the electron is present at top side or electron present on the bottom side, whatever it may be. If the electron is present on the top side, see that the PZ atomic orbitals are perpendicular to each other. PZ atomic orbitals are perpendicular to each other. Therefore, they will not along the line or along the axis. Therefore, during the covalent chemical bond formation, now the lateral overlapping that occurs. Therefore, the lateral overlapping of the sigma, that is a half-filled atomic orbital, that leads to the formation of the pi covalent chemical bond. This is called carbon-carbon pi covalent chemical bond. Whether it may present above the plane or below the plane, whatever it may be, not two at a time. Therefore, this is called as a pi covalent chemical bond. I will introduce the new term pi covalent chemical bond. Whereas a pi covalent chemical bond is formed by the lateral overlapping of the half-filled atomic orbitals. Whereas only in the presence of the p atomic orbital has ability to form the pi covalent chemical bond. The overlapping of the s atomic orbitals are not involved in the pi covalent chemical bond formation. Therefore, very important, s atomic orbital overlapping not leads to the formation of the pi covalent chemical bond. sp atomic orbital overlapping not leads to the formation of the pi covalent chemical bond. pp overlapping, either px or py or pz atomic orbital overlapping only leads to the formation of the pi covalent chemical bond. Therefore, in entrance exam they will ask the questions like this: which one of the following half-filled atomic orbital has ability to form the pi covalent chemical bond? They may ask ss overlapping or sp overlapping or pp overlapping or sd overlapping, whatever it may be. Very important, p and p atomic orbital overlapping that leads to the formation of the pi covalent chemical bond. This is very important. Whereas ss atomic orbital or sp atomic orbital, that leads to the formation of the sigma covalent chemical bond. Sigma covalent chemical bond. Therefore, see p and sp2 pp overlapping. This is sp overlapping. This is pp overlapping, lateral pp overlapping, axial. Therefore, how many pi covalent chemical bond? Don't predict it as a 2. Either it may be present above the plane or it may be present below the plane. Don't predict it as 2 numbers. Therefore, plus one number of pi covalent chemical bond. Pi covalent chemical bond. one number of the pi covalent chemical bond. Now, very important question. Mention the differences between pi covalent chemical bond and sigma covalent chemical bond. There is a axial overlapping of the half-filled atomic orbitals that leads to the formation of the sigma covalent chemical bond. Lateral overlapping of the half-filled atomic orbitals that leads to the formation of the pi covalent chemical bond. Sigma covalent chemical bond is stronger than pi covalent chemical bond because axial overlapping is more efficient than lateral overlapping, or lateral overlapping is less efficient than axial overlapping. During all chemical reactions, whenever this type of the pi chemical bonds are involved, the classical reactions are addition chemical reactions because rupture pi covalent chemical bond first ruptures sigma covalent chemical bond, rather they are involved in the chemical reactions. Therefore, in all organic chemical reactions where we have the unsaturated molecules, like multiple bonds are there, like alkene series and alkyne series molecules, usually they possess a pi covalent chemical bond in the structure. Therefore, the classical reactions of the unsaturated hydrocarbons which contains the multiple bonds like pi covalent chemical bonds within the structure, they are addition chemical reactions. We can add the species into the reacting molecules. We can't remove. Therefore, very important. This is about the structure of the ethylene molecule. Now, what about the bond angle here? That is equal to 120 degree. This is corresponds to the planar bond angle. Here, this is equal to 120 degree. That corresponds to the planar bond angle. Therefore, very important. Bond angle. There is a hydrogen carbon bond angle, that is 120 degree. This is hydrogen carbon bond angle. Hydrogen carbon bond angle, that is equal to 120 degree. And S character in sp2 hybrid molecule, that is equal to S character, that is equal to 33.3%, and P character that is equal to 66.7%. This is very important with respect to the sp2 hybrid atomic orbitals. Okay, this is about the hybridization of sp2 hybrid molecules. Now this is pi covalent chemical bond. Very important. Sigma covalent chemical bond and pi covalent chemical. Covalent chemical bond formed by axial overlapping. This is very important word. Axial overlapping of half-filled atomic orbitals. Very important. Pi covalent chemical bond. Very important for exam point of view. Covalent chemical bond formed by lateral overlapping of half-filled atomic orbitals. Now this is very important. This is lateral overlapping. This is axial overlapping. This is lateral overlapping. Lateral overlapping. Sigma bond is stronger. Sigma bond is stronger than pi bond. Sigma bond is stronger than pi bond. Pi bond. Sigma bond is stronger than pi bond. Reason, this is very important. Lateral overlapping is more efficient. Lateral overlapping is more efficient than axial overlapping. Axial overlapping is more efficient. Axial overlapping is more efficient than lateral overlapping. Lateral overlapping. Axial overlapping is more efficient than lateral overlapping, or lateral overlapping is less efficient than axial overlapping. During all chemical reactions, wherever pi and sigma both are involved, pi reacts first followed by sigma. Therefore, the classical reactions of the chemical compounds which contains the pi covalent chemical bonds are usually addition chemical reactions. Okay.